Hi, so today I'm going to go over using DFAs to solve a couple Leetcode problems quickly and easily. So the problems themselves might be pretty difficult, they're marked as hard, but this method makes it a lot easier to solve them and is applicable to a wide variety of problems. So I'll just get right into it. So here's the problem overview, and here's like a general definition of the problem. So we're given a series of conditions for the validity of a string, and we're given an integer n, which is supposed to be the length of the strings. And we want to return the total number of possible strings of length n that obey all of these conditions. So like, for example, we're given n, and say we want the number of strings of length n that are composed of characters a and b, and that don't contain AAA as a substring. So here's the intuitive line of thought. Just try everything, right? So brute force method, try all strings and exclude those that contain AAA. So in this case, there are only two possibilities for each character. So we'll have a runtime complexity of O of 2 to the n. It's not really an issue as long as n is less than 30 or so. 2 to the 35 is about a billion. Actually, it's 2 to the 30, sorry, is about a billion. So a fast computer should be able to do that pretty quickly. So here's the code for that. Import time just to see how long it takes. Then we've got our function count valid. And basically what we're going to do is just for ease of coding and just to make things easier, we're going to map binary 0 and 1 to A and B because we just have two possibilities for each character. So we're going to iterate through all possible possibilities there for the length of our string. And the way we'll do this is by using some little bitwise logic. We'll start at 0 and then we'll go up to 1 less than 2 to the n. And then we'll check whether the string AAA, so without loss of generality, we're choosing to say that 1 equals A here. And we'll sum up all those strings into the total and then return that. So here the idea is really we're just using binary to simplify this iteration. So for example, for like n equals 4, we have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, etc., all the way up through 1, 1, 1, 1. And this is it's an easy way to get all the subsets of a set, right? Basically, all possible combinations of 1s and 0s. But we see this ends up taking a bit too long. So for 10, it's very fast, right? It's 0.0 seconds. 20, it's a bit slower, still much less than a second. 25, it starts getting a bit much, right? It's like over 4 seconds. And then when we're at 30, it's like over 2 minutes. So it's really not good enough. And it's even worse because on Leetcode, the constraint on n is like 2 times 10 to the 4th, which would take on the order of 2 to the 2 times 10 to the 4th, or about like, this is like an insane number, 10 to the 6,000 something iterations, which is even going to be worse in practice because we need to check that the substring is contained, right? So in our example, we have AAA. We would need to check substring containment. That's going to be O of n as well, so it's even worse. So here's the new method we're going to look at, which is the use of DFAs. Here's just a screenshot of the Wikipedia for that. So there's a lot of theory around that. I'm not going to go too in depth on DFA theory, but I'll just talk about how we can use them. So back to our AAA example with A and B. Here's the state machine that we create for that example. So we start at the start state. If we see an A, we progress to the state where we've seen one A. If we see another one, progress to the state where we've seen 2 A's. And if we see a third one, we progress to the state where we've seen 3 A's. And then we just stay in this state regardless of what we see. If we see a B, we don't change our state at all because B's are not relevant for us, right? All we care about is the quantity of A's. And then you'll notice that these 3 have double circles around them, and this one does not have a double circle over here. This last one, so the triple A one does not have a double circle, but all the other ones do. That's because the triple A one is not a valid string, right? If we ever make it to this state and we get stuck there, then our string is not valid. But for the other ones, they're all valid. Actually, this example is a little bit off because this would just be whether we've seen 3 A's. So my bad. Yeah, so assume rather than seeing a string of 3 A's, this is whether we've seen 3 A's in the string. Actually, you know what? Let me just fix that. Okay, so I fixed that mistake. So yeah, now this should make a bit more sense. So from the start state, right, if we ever see a B, we don't go anywhere. Then if we see an A, we go to the state where we've seen 1 A in a row. We see another A, we've seen 2 A's in a row. We've seen another A, we've seen 3 A's in a row, and we're stuck, and we're in the dead state now. If we ever see a B in A or AA, then we just return to the start, right? Because we start counting again from 0 A's seen in a row. So this should make sense. And yeah, so this is called a DFA, or Deterministic Finite Automata. So here's our first example of a problem that we'll look at. This one is student attendance record 2. It's marked as a hard problem. And so here's the description. So an attendance record for a student, blah, 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 blah. Basically, we have a string which can either have A, L, or P as the characters. And then we return, the string is good if the number of A's is strictly fewer than 2. And we never see 3 L's in a row. And then, big number, right? So we'd want to return it mod 10 to the 9. But that's not really relevant for our purposes, so we'll just ignore that. So here is the state machine for that problem. So again, no more than 1 absence the entire time. And if we ever see 3 L's in a row, that's also not allowed, right? So here, we start at the start state, and if we ever see a P, a present, right, we just don't go anywhere. Next, if we see an L, right, this is going to be the same as our AAA kind of thing, right? So if we see an L, we've seen 1 L in a row. If we see another L, that's 2 L's in a row. If we see a third L, we're in the dead state, is what I'll call it. And from each of these L states, if we ever see a P, we go back to the start, right? We start counting from 0. The one thing we do have to remember, though, is if we see an A, we can never go back to not having seen an A, right? So if we see an A, then if we see present after that, we stay in the A state. And then if we see an L, now we're keeping track of 2 things at once. We've seen an A in the past, and also we've seen an L now, 1 L, right? So if we see another L, that's 2 L's. If we see a third L, that's 3 L's. But also in any of these A states, if we ever see another A, then we immediately go to the dead state, right? And then there we just stay, ALP, either of those, any of those will just stay in that dead state. Okay, so hopefully this should make some sense. And so now we want to actually convert this into an answer. So what we have is we have the graph of all possible states with regard to the validity of a string. And what we want is the number of possible paths from this start state here to any of the valid states, right? So that means any of the states of the double circles. So that's start or L or LL or A or AL or ALL, but not dead, right? So really it's just anything besides the dead state. And you want these to be of length n. So first what we'll do is we'll convert our DFA to an adjacency matrix of states, right? So we can go from start to start, we can go from start to L, and we can go from start to A, but we can't go from start to LL, or start to AL, or start to ALL, or start to dead, right? So this is just, we put a 1 there if there's a transition from this side to this side, right? So from the row to the column, we put a 1, and otherwise we put a 0 there. So this is just the adjacency matrix. You'll be familiar with this if you're familiar with graph theory, or if you've done any graph Leetcode problems before. So now what we're going to do is we're going to take the nth power of this matrix to get the total number of length n paths from I to j in each ijth entry of the resulting matrix. So I'll go over the proof sketch of this later. But here we've got some octave code that's actually going to run this. Octave because it's really easy to do matrix stuff there. And so here's our matrix, and now we're just going to take a to the 30. That gives us this result. And now we want to sum the top row except for the dead column, right? So the dead column is over here. And this is the code for that. And we get this as our answer. So it's like around 2 billion. So now let's talk about the proof of this method. So in the starting matrix, we basically have a number of length 1 paths, or that's exactly what we have, is a number of length 1 paths from I to j for all I and j, right? So if there's not a path there, then it's 0. And if there is a path there, then it's 1. And then in each time we do a matrix multiplication, here's what we get, right? So now the new value of a ij, that ijth entry, is going to be the sum from k equals 1 to n. So that's all possible nodes k, right? Intermediate nodes k, where we have the paths from I to k, and then we're multiplying that by whether there's a path from k to j, right? So basically what this is doing, we have at this point the sum of all paths from I up to other nodes k, right? And now we want to take the sum of all paths from those nodes back to j, because what we care about is really from I to j. And we'll only do this if there is a path from k to j, right, in one step, because that'll be 1 if there is, and otherwise it'll be 0, and we won't count that. So this is basically, you know, this is our base case up here, the length 1 paths. And then in this matrix multiplication, this explanation is basically showing that if we have p, then we have p plus 1 satisfied, or if, I guess, n and n plus 1 for that predicate. So this is basically a hand-wavy inductive proof, but the logic is there. So now here's our solution code for Leetcode 552, the student attendance record problem. First we'll import NumPy. This will make it really easy to multiply matrices. Next we have, I'm just going to set n equals 30 because this is what we're testing with. And here's our matrix. And you'll notice I have d-type object here. This is because NumPy by default uses, I think, either int32s or int64s. Either way, that's going to overflow pretty quickly. So we don't want to restrict ourselves to that. We'll use d-type equals object, and that'll allow us to handle like 4,300 digits of result there, which is going to be more than enough. Next, we'll find our matrix of paths, the number of paths, which we'll use numpy.linalg.matrixPower for. And that'll be a quick and easy way to do that. And then we'll sum up the quantities in the first row, except for the dead column, right? So in this case, dead is the index 6. And then we'll just print that out. So this gives us exactly the same as what we saw in Octave, right? A little under 2 billion. So let's talk about the time complexity here. So the time complexity for matrix multiplication is O of n to the k, where k is like less than 2.5. So by default, it's O of n cubed. And the way that you learn to do it in school is probably O of n cubed. But recent research, or I don't know how recent, but there's research that's brought it down from 3 down to like 2.37 or something like that. And you know, we're using NumPy here, right? It's going to be using an efficient method to do this. And the time complexity of a matrix power a to the p, where a is n by n, is O of n to the k log p, right? So here's the general idea behind that. Say we have a to the 9th, right? In reality, we only need to do like 4 matrix multiplications, right? We do a times a, that gives us a squared. Now we do a squared times a squared, that gives us a to the 4th. We do a to the 4th times a to the 4th, that gives us a to the 8th. And then we just multiply that by a, and then we get a to the 9th, right? So, and if it were a to the 8th, then it would just be 3 multiplications. And so that's why you can see it's going to be log base 2 of p there for whatever power p. That's the total number of multiplications we need to do. So in practice, our matrix has 6 states. We'll exclude the dead state from the matrix multiplication. because it is it's an absorbing state in our it's not really like a Markov chain, but basically we can just exclude that there, as it doesn't have paths back from the dead state. Then p, or n in the problem definition, is going to be about 2 times 10 to the 4th. So log p is going to be about 14. And then the overall time complexity, it basically ends up being O of 1, since the constants are so small. But in practice, it ends up being a bit longer because we need to import NumPy and we need to like set up our matrix multiplication stuff. Yeah, and Leetcode has time that it uses to actually process the solution as well. So now let's go to another example. This one is 1220, count vowels permutation. You'll see this one is similar kind of thing, right? So we're given an integer n, and we want to count the number of strings of length n that can be formed using these rules. So here, every character is a lowercase vowel, so A, E, I, O, or U. A can only be followed by E can only be followed by A or I can be followed by anything besides I, O can be followed by I or U, and then U can only be followed by an A. So these complicated rules, they're not that complicated, but basically they govern, whether something can be followed another thing, and anyway. So here's our DFA for that. I color-coded things. Apologies if it's a little bit difficult to see, but here's the gist of it, right? So we've got our start node, and we've got A, E, I, O, or U, depending on what we've seen so far. And then if we see the wrong thing, then we go to our dead state. So here's our matrix, and I actually chopped off the dead state here because it's not really relevant to the problem. But we really just care about the connections among the live states. And here's the code, right? So we just take that matrix, we plop it right into here, into our NumPy array. And here I've included the Leetcode boilerplate stuff as well. So here's mod this, right? And then we literally just put this matrix in, take the matrix power, and then sum the top row of the matrix mod that value. So in conclusion, our process is to first create a DFA representing the valid strings. Then we want to convert that DFA to an adjacency matrix representation. We want to take the nth power of that matrix, and NumPy is efficient doing that, so we use NumPy for that. And then return the sum of the top row, just excluding the invalid or dead states. And so here are a couple exercises to take with you once you finish watching. So first, do your own research. Make sure that you actually understand the logic behind adjacency matrix powers. I gave a proof sketch, but you should try and make sure you understand why that actually works. Next, what if the conditions are probabilistic, right? So validity conditions, maybe they depend on a random variable. Maybe like if you see an A, then sometimes it's invalid, sometimes it is valid. Maybe it depends on other parts of the string. So think about that. And then what about checking for palindromes, right? So why can't we use this to check for palindromes? Answer, we actually can't use this to check for palindromes, and for that you would want to research the pumping lemma. Basically, a DFA can only have finite memory that it holds. It's a deterministic finite automaton, and if we have a string that's long enough and has certain characteristics, then we can trick the DFA into actually accepting palindromes. So maybe do some research on that if you're interested. But yep, that's been it here, and yeah, let me know if there are any other fun video topics you'd like me to look into. And see you next time.